Hello, everyone. Hello, sir. Can you hear us?
Yes, yes.
Yeah, good afternoon, sir.
Yeah,
Yeah. Yes, so we will introduce you first and then we will start the session. Yes. Okay. So let me welcome Professor Bhaskar Kansari, who is the professor in the IHFSC, chair professor in the Department of Physics at the Indian Institute of Technology, Delhi, and a joint faculty member at the Optics and Photonics Center, OPC, at IIT Delhi. With more than 18 years of the academic and research experience, he is recognized as one of the India's leader experts in quantum science and technology, quantum optics, and optical communication. Professor Bhaskar completed his PhD in physics from the University of Delhi in 2011, jointly carried out at the National Physical Laboratory, New Delhi, where his doctoral thesis explored the coherence and the polarization properties of the optical fields. He holds an MSc in Physics 2005 and a BSc in Physics, Mathematics and Computer Science in 2003 from the Kumaon University SSJ campus, Almora. He further enriched his expertise through the postdoctoral research at two leading institutions in Europe, the Institute of the Optic, Belgium, France, and the Max Planck Institute of the Science of Light, Erlangen, Germany. His research interests span a broad spectrum of quantum and optical physics. He has led pioneering work in the quantum secure communication, demonstrating India's longest fiber and the free space-based QKD experiments. He is advancing entanglement-based quantum networks at IIT Delhi and has made a significant contribution in quantum optics and nonlinear optics, including the development of single and entangled photon sources. Schrodinger cat states and the macroscopic Bell states and advanced quantum tomography methods. His work also includes experimental studies in the optical coherence and polarization, interferometry, and plasmonics, with the application to the quantum imaging and secure communication. Professor Kanseri has authored more than 75 peer-reviewed international journal publications and delivered over 160 conference presentations and invited lecture worldwide. His academic contributions have been widely recognized. He received the Teaching Excellence Award in 2022 and Wien Arora Early Career Research Award in 2022 from IIT Delhi. He has elected as a member of National Academy of Sciences, India in 2023 and Associate Fellow of the Indian National Science Academy, INSA, in 2023. Thank you, sir. Welcome you in this QT series. So now I'm handing over to you. You can start your session.
Okay, so I have two talks. So is there some question answer in between or how it is going to be?
Yes, so sir, we will break this complete 2 to 4 session into streams. So in 1 hour, you can take, it's up to you, you can take in between when you think, okay, topic is completed, you can see the, we will help you to see the question and answer in between. And there will be a break between, after 1 hour of 5 minutes.
Okay, perfect.
Okay. Yes.
Okay, so can you see my screen?
Yes, sir. Yes, sir.
Okay, good. Okay, so first of all, I would like to thank the Academy MNIT Jaipur for giving this invitation, and I'm very happy to be here and to give you some ideas about what we have done over last 5 to 7 years in quantum communication, and also what is our plan for next decade or so in exploring the various aspects of quantum secure communication. So as you all know that when we talk about quantum communication, in fact, I have seen the agenda and there has been several eminent speakers prior to today's talk. So a good background on quantum communication must be set up. However, I would like to divide my 2-hour session into two sections. In the first section, which is I titled as Quantum Secure Communication and Secure Key Distribution, Here I will mainly focus on the basic ideas behind developing these quantum technologies and what kind of benefits quantum communication can provide, what is the need of doing that, and what kind of activities people have done in state of art in the area of fiber-based quantum communication. In the second part of my talk, I will basically focus on some of our works where we have attempted to demonstrate both in lab and in field scenario fiber-based quantum communication. In fact, a lot of our activities have been in free space quantum communication, including entanglement-based communication. But I will try to restrict myself to fiber-based communication because I think in free space already there has been several talks in past. Okay, so I'm going to talk about quantum secure communication and secure key distribution in the first session. So as we all know that if we go back to the last century, there has been tremendous activities in the area of quantum mechanics or quantum science. In fact, at the end of 20th century, there has been significant developments which demonstrate that what kind of potential quantum mechanics or quantum physics has to develop these kind of quantum technologies. And if we go back 100 years before, when there was no quantum mechanics, people have been exploring classical physics to a great extent, and they had the opinion that almost all kind of problems have been solved or taken care of, and there is nothing left which we really need to look into in the area of classical physics. However, there were certain limitations of classical physics, especially in explaining black body radiation or some related light matter interactions where the existing models like wave theories were not working. And at that time, there were a series of proposals and experiments which were mainly led by either Max Planck or Einstein or their colleagues, who have really looked into the area of a new kind of science or a kind of new kind of mechanics, which essentially deals with microscopic domain, not the macroscopic domain which you essentially look into. So this microscopic domain leads to a new kind of science or a new kind of mechanics, which we call quantum mechanics now. So during the last century, that is the 20th century, there has been attempts to give new basic rules that govern the physical reality, and then to understand the existing science. So it has been a great revolution conceptually because it gave us several understandings about the structure of matter, its properties, and its interaction with light. So if you see here, several of the devices which we are using nowadays, which include, for example, computers, smartphones, semiconductor technology, nuclear
Hello,
energy,
sir.
and yes.
No, no, no. Now it is clear. So actually there was pop-up, so now it is clear. Yes.
Okay.
This is fine now. Yeah.
Okay, perfect. So all these devices were the outcome of this first quantum revolution we call, or in other words we call it quantum 1.0. In fact, I would like to mention that two major developments which were in the form of lasers, which nowadays are almost in every walk of life, including the pointers in your teaching room or the laser cutting machines, or even high power lasers for as a weapon for strategic forces. Lasers are everywhere and they are the outcome of the quantum 1.0. Similarly, the transistors, which have really led to this revolution to miniaturize smaller and smaller in sizes. This all has been because of the first quantum revolution. In fact, now if you look, almost major ideas has been understood, and people have started to customize what was the outcomes. And this customization essentially leads to what we call the second quantum revolution. And in 21st century, essentially we are using quantum mechanics to change the face of the physical world and to design in our own way, for our own purpose, a new kind of technology which are disruptive in nature, and that's why they are called disruptive technologies, or in other words quantum 2.0. So these are the list of some of those technologies which are aiming. It includes different colors, so the colors are essentially the time scales over which we are looking into. In short term, we have already demonstrated several ideas into practical applications, including quantum communication, quantum cryptography, quantum teleportation, or even entanglement. Small quantum gates have also been developed. And in the medium scale, like next 5 to 10 years, we are aiming to have quantum sensing and quantum metrology to be very much in the domain, which also includes quantum imaging and quantum radars. And in the long term, probably next 10 plus years, the goal is to develop not only quantum computers, which are error free or fault tolerant, but at the same time to look for quantum foundations where many of the discoveries which could happen using these extreme resources such as quantum computers. So the basic motivation behind these developments has been one of the major factor has been the miniaturization, because as I mentioned, the transistors led to miniaturize big mainframe computers into small pocket computers. But then again, the question is how small we can go. We can keep going smaller and smaller, but ultimately we will be limited by Planck's constant, Planck's length, where we really need quantum principles to explain everything, because classical physics cannot do so. And also the development of these technologies are offering us vastly improved performance compared to their classical counterparts. And in fact, a lot of organization and control of complex systems can be done using the laws of quantum physics. And this is why there are several kind of quantum technologies which have been developed over the last decade, which include some multi-qubit microprocessors, which are either by Google, IBM, IonQ, or Intel. In fact, their qubits are increasing with time. There have been developments in quantum sensing. If you are aware about LIGO, that is Laser Interferometer Gravitational Wave Observatory in US, they have come up with an idea of using this quantum light, which we also called squeezed states of light. And by using that, they have increased the sensitivity of these interferometers by 2 to 3 times. And in fact, this is leading to more and more observation of astrophysical events. And also because quantum computers can be a threat to the existing security solutions, a new kind of security solution called quantum key distribution has come up. And China, for example, has shown satellite based quantum communication for more than 1,000 kilometers using this technology. So essentially we are leading from quantum mechanics to quantum engineering. And in today's talk, I am going to focus on this quantum key distribution. This is a picture which essentially give you the idea of what kind of applications we can look for quantum physics in strategic areas like warfare. So we have quantum computers where we can have several applications as quantum cyber warfares. We can have quantum communication where we can use securely communicate among different stakeholders. At the same time, quantum radars are being developed which can uh, look into stealth objects like the stealth aircrafts or stealth drones. Quantum magnetometric sensing is coming up where we can sense small and small magnetic fields leading to detection of several kind of underwater warfares. We have also electronic and navigational warfares which are getting better and better using quantum techniques. One can use quantum chemical detection and quantum underground mapping using those techniques. So essentially in almost all areas of warfares, quantum is becoming a very, very major player. Quantum computer, as I mentioned, the existing cyber security, which is currently being used, is in at the stakes, because with quantum computers, one can essentially break those codes. So people are coming up with different type of attacks. If you have seen these news in last 2 3 months, that there are attacks like harvest now, decrypt later, where people are storing all these codes in some safe places so that they could use them to decrypt once the quantum computers are available. And it is expected that next 4 to 5 years there will be sufficiently strong quantum computers which can break those codes, and then the informations would be available to the hackers. At the same time, China has developed military grade encryption breaking methods using quantum computers, which is opposed to new kind of threats to the West. So this all tells you that this is quantum security, which is one of the need of the hour because of such kind of cyber security problems. So if you look into quantum communication across the globe, there are several ways it can be done. One uses fiber-based communication, which I will focus in my today's talk. However, free space and satellite-based communication are other alternatives which can use either satellites as a trusted nodes or even a line of sight kind of communication. And if you see here, these are the networks, quantum communication networks, which are developed either using fiber-based communication or using free space or satellite based communication. So in fact, QKD is not only just for science, but it is all for applications and its implementations. So in the market, the requirements are huge. If you see, a key expected market of 20 billion US dollars is in next 5 to 6 years. There are several users which include data centers, infrastructure utility users, providers, telecom providers, mobile and payment system providers, and even militaries. All are going to use these very, very sophisticated quantum cybersecurity applications. Uh, in order to develop those, one needs to make a complete ecosystem, and that supply chain based ecosystem would require not only just quantum sources or quantum photon detectors, but also several allied technologies, which include such as the cryogenic systems, because many of these devices require sub-Kelvin temperatures. There could be the requirement of QRNGs, which provide random numbers, quantum computers, and quantum sensors. So essentially, a complete ecosystem needs to be developed, and that enabling technologies would be a requirement or an avenue even for the students or the people who are working in these domains. Since many of these technologies are of denied nature, that means a country would not provide it to the other country because of the national security. Every country has its own plans to develop their own quantum technologies. And if you see here, there has been several million US dollars which have been proposed by every country to develop their own indigenous technologies. India has its own quantum mission now called National Quantum Mission, and I'm sure that you must have heard from people about what kind of avenues you have. So essentially, there are tremendous avenues in almost all domains, whether it is academics, whether it is prototyping, whether it is industries. In fact, startups and industries are more and more focused in these kind of missions so that the new technologies can be translated to markets. So I would invite you all to be a part of these kind of national initiatives so that many more things could be done in developing these technologies. So now in today's talk, I am going to focus about the need of quantum cryptography. What is QKD and what is its essential? I will just highlight because I'm sure that you have already a good amount of background in these domains. What kind of current approaches for QKD are being used, and what are the challenges associated with secure communication? And finally, I would provide some highlights and summarize my talk. So cryptography, as we know, that is a way to disguise the information so that any unintended recipients do not get it, and they do not understand what is the information. So both ways the cryptography needs to be done. In quantum cryptography, the goal is not to use the mathematical problems because the quantum principles themselves provide a uh, basic kind of security, and in fact it is so strong that no computationally capable device can break these kind of codes. So uh, we are going to use this quantum cryptography for securing our communication systems. If you look into the existing security methods or encryption methods, there are two ways the encryption is done. One is called symmetric encryption, where the sender and the receiver uses the same key for encryption and decryption. So that means that an identical key needs to be distributed from one user to other user so that any message which is encrypted by that key can also be decrypted by that key. So there are ways where by which we can do that, and they are called trusted couriers. As of now, they are used for distribution, but this is a very slow method, and trusted couriers are the ones whom we are trusting. If they become untrusted at some point of time, all our keys would be basically eavesdropped, or they will be compromised. So we really need to get rid of this trusted courier thing, and I will show you later that how quantum cryptography provides a way to do that. We use one-time pads also to distribute that. You must have received one-time passwords, which nowadays you call it OTPs, for encryption and decryption, and using that there is an authentication which happens either for a credit card transaction or for any kind of password-based transaction. It is a faster methods because we are using only one key for both cases, and it uses very low amount of resources. And the good thing is that if you do it at one time, because as the name says, then it is information theoretic secure. That means nobody can break it. However, in case of digital communication or internet communication, this is not going to be used, because here we need much more secure systems, and a larger security requires a longer key and a more random key. And for that, one uses a public-private kind of encryption, where there are two keys: a public key for encrypting the data and a private key for decrypting the data. And it is called asymmetric encryption. Here one uses some very complex, computationally complex methods for making the key or breaking the key. And these methods, if with existing computational power, or the supercomputers would be requiring ages, probably hundreds of years to break. However, if there is a new machine which comes and which breaks it in a fraction of a second, then it's a big problem for asymmetrically encrypted systems. That means all internet and digital world. And this is why quantum computer is going to be a big problem, because if it comes and it breaks all these because of its very order of magnitude larger computational capability, then all your security systems will be vulnerable. And here the solution comes from what we call with the new kind of encryption, that is called quantum key distribution. Here one uses the principles of quantum physics. So Alice and Bob are the typical users, which are the legitimate ones, and Eve is the eavesdropper, which is trying to steal the information. So one is using the principles of quantum physics to transfer the information, and anybody who is trying to eavesdrop essentially changes the information or the signal in a way that Alice and Bob immediately know that a change or interference has been happened. It means somebody has steal the information, and they can accordingly take steps. So clearly you see that the method is going to be very different than the existing methods of communication or a key distribution. So this is a typical another way to explain it. So we use an encoder which is encoding the message, say Alice, another decoder which is decoding the message, that is Bob. We are using a channel which is called quantum channel, by which some quantum property or quantum object is transferred. Since the largest speed by which we can make communication with photons, because they have a speed of light equivalent to c, you could see that one can use a quantum channel such as a free space channel or a fiber channel, where the photons can be sent. Now these photonic qubits, which we call, some degree of freedom of these photons can be basically used to encode the information. This can be either a polarization property, that means you can use either horizontal polarization, vertical polarization, or its superposition. You can similarly use orbital angular momentum, or you can also use time waves. So no matter whatever we use, this is the encoding mechanism, and a particular degree of freedom is encoded. Then it is decoded at Bob's side. With public channel, you can make some communication, and that way the whole process happens, and the key is distributed securely between Alice and Bob. Now there are several ways to understand this. So this is another way to understand that how Alice and Bob essentially communicate. In fact, the good thing is that there are set of protocols or rules by which you can do the communication. You can say share their keys, and that way you can be secure. They are either using single photons, where we have protocols such as BB84, B92, or decoy state protocols. And also we have some phase-based protocols which are either using differential phase shift or distributed phase shift or even coherent one-way protocols. One can also use another interesting property called entanglement. I will explain it later in my talk. And there are protocols such as E91 and BBM92 which can be used for communication using entanglement. What essentially one looks is two important parameters. One is the key rate, where you know about either the raw key rate or the secure key rate depending on how you do the post processing. And the other thing is the quantum bit error rate, which essentially also called QBER. It is a parameter which tells that how many of the keys out of the 100 keys which were sent have been wrongly received by the user. And that gives us the QBER. This number needs to be some threshold. For example, for BB84, it is 11%. And if you have error more than 11%, then you understand that somebody has eavesdropped the system, and that way you can catch the eave. So this is another way to understand what is the post-processing scheme. So first you send the photons from one to another, and you have got something what we call the raw key. And once this process has happened, several mathematical operations needs to done at each party, including the authentication, so that you first identify that the user you are talking is an authenticated user. Then you use shifting, where you essentially look for the basis based depending on the protocol you are using, and you only take those keys which are using the current basis. And then you do information reconciliation and privacy implication in order to improve, in order to remove the errors and improve the security of the key. And that finally gives you the keys which are final keys, and they need to be same at both parties, and this way the key is actually distributed. Now, in case of quantum communication, there are several basic physics principles which essentially play a very important role. One of them is called no cloning theorem. So in case of classical communication, for example, you can always clone a page of information. You can use a photocopy machine and make hundreds of copies of identical information. However, this is forbidden in case of quantum, because the initial basis or the arbitrary basis is not known. If it is known, let us say it is vertical polarization, you can always make several copies. If it is horizontal polarization, you can always make several copies. However, if it is a 45-degree or some arbitrary angle, then since you do not know in which basis it is prepared, then every time when you try to project it, you lose the information, and that way the cloning is not permitted in quantum states. And that's why that any eavesdropper cannot make copies of the information. The moment it makes a detection, the basis is already projected, and then the previous information is completely lost. And an example is using quantum states using single photons, because in case of single photons there is one photon at a time, and if you try to make a copy of one photon, it is not allowed. On the other hand, imagine if you have a state which has more than one photons, then one can always use a experimental device called a beam splitter, which splits these two photons in two paths. Alice can send these photons, Eve will take one photon out of it and send the other photon to Bob. And this photon which is available with Eve can be used to steal the information. So clearly that one important requirement for when we are using photons in case of quantum communication is that you need to use only single photons. Multi-photons are very bad. And if you have multi-photons, one can make photon number splitting attack, which I just explained, and that way they can extract the information. Now, if you look into what kind of quantum states we need to prepare, there are several ways you can characterize these states or even the sources. So if you have a thermal source, which is basically a source where the light is produced by its temperature, an example is all the stars or all a tungsten lamp, for example. So in case of thermal sources, you see that the statistics is Bose-Einstein and the correlations are bunching essentially means then photons are always coming together. So if the photons come together, then the photons are always in multiples bunches of multiple photons. So one can easily attack and take out of the photons. So that's why the thermal sources are not good for quantum communication. One can use lasers. A laser has a statistics which is called Poissonian. If you see, this is sharper than what I explained now. And in case of this green Poissonian, you see that the distribution has a random kind of statistics. That means that the photons can come anytime. So the multi-photon probability will still exist. It will be lesser than the thermal one, but it will still exist, and that can also be a problem sometimes. And this is why we always, in many times, we also prefer not to use lasers for using quantum communication. And the third important category is what we call sub-Poissonian ones. And you see that the sub-Poissonian is the blue one, which is even sharper than the Poissonian one. And this is the sharpest probability distribution, which says that the photons are always anti-burst. That means the photons are arriving always far from each other. So at a time, there is a probability of only one photon. If you try to measure two photons, you cannot measure because there is no two photon available there. So such kind of sources, which are either single photon sources or even entangled photon sources, are the preferred choice for doing quantum communication or for preparing these kind of quantum communication outcomes. I have also explained the same thing here, that how the statistics is anti-bunched, random, and bunched. And as you see that in anti-bunched, in a particular window, the probability of having photons is very less, and you can get only one photon at a time on average. Whereas in other cases, there could be many photons in that window, and that way they can be used for different applications. In case of quantum communication, we prefer to have anti-bunched sources. Now, how these sources can be developed? So you see that one can easily make a Poissonian source from a laser. You can attenuate the laser significantly. A laser pointer can be attenuated by placing a glass block in front of it or some semi-transparent object in front of it, and that way the number of photons can be reduced. However, as I mentioned in the previous slide, it still follows the Poissonian statistics, so it will have non-zero probability of having multiple photons. That means sometimes you may get few photons together, and that way they can be prone to what we call the attacks associated with multiple photons. Now there is an important understanding about wave particle duality. Many of you must have studied this in your 12th or in your first year classes. So if you see here, the light itself, like photons, these are the quantum objects, they behave sometimes waves and sometimes particles. So if you see here, if I have a laser beam and I pass it through a double slit kind of setting, you will get the interference pattern, and this interference pattern is essentially somewhere the intensity is higher, somewhere it is lower. So these two pinholes are essentially giving you light. You are adding two lights, but you are producing somewhere light and somewhere dark. And this is something which is very, very strange phenomena, and it is called interference pattern. Now, if you use the particle property, like that you are sending small balls through these double slits, then you will see that the probability of occurring these balls in front of each slits would be maximum. So basically you will get two peaks, not an interference pattern. So these are the interesting properties of waves and particles. However, if you do the same with a single photon source, I have a source which gives you one photon at a time, and I put a double slit. So the photons will actually pass through both the slits simultaneously, and it will give you an interference pattern. So this is a very, very unique example of wave particle duality, because despite the nature of photon being particle here, it is producing a phenomena which is called a wave-like phenomena, like interference pattern. Similarly, in the same setting, if by any chance you try to look into the holes, these two holes, where from which path the photon is traveling, then the photon will reduce from this wave property to a particle property, and you will only get these two peaks, which were the feature of the particle nature. So one can look into such experiments. In fact, one can develop such experiments. If you see in this slide, I am showing you a small video where we have made a single photon source. Essentially, we used a laser, we attenuated it significantly, though it produces single photon at a time, and the photons are so low that the distance between them is few hundreds of meters. That means the photon cannot interfere with other photon. Now, if I'm passing it through a double slit and look into the screen, what kind of pattern is expected when we are sending one photon at a time? So one can simply think of that it will be a two peak kind of thing, because each slit will have its own peak and you will not get any interference pattern. So this left side, if you see this screen, this is a screen which is placed at this recording plane, and it is a CCD, which is called charge coupled device, which can sense single photons. And what small dots of white color you see here, these are the dark noise or some spurious photons which have already been detected by the device. So I will run this video if it works, and we will try to see that what happens when with time we record these outcomes. So you see that now the video is running and we are recording these photons which are arriving on the screen, and it is recording for a quite long time because the number of photons are very less. So if I keep recording it, you will see that at some point of time a small lines will start appearing. So these are the dark regions are the minimage and the bright regions are the maximage. And in fact, if I could go, just I will try to see if I can run it faster. So if I go for longer run and accumulate for few minutes, you will clearly see that the photons have demonstrated these single photons have demonstrated a wave-like phenomena, that is an interference pattern. So this is a direct pedagogical evidence that the single photons can produce these kind of interference fringes. Okay, so since I have very less time, I would skip further. And so what is actually happening that since nobody is trying to look into the path of the photons, the photons are acting like wave. They are interfering with themselves and producing these interference phenomena or interference patterns. So let us go further, and I already mentioned about single photon sources. So let us move further and try to see that how can we generate these single photons. So one method is called spontaneous parametric down conversion, and in this method, as you see, we have an intense pump beam which interacts with a crystal which is a nonlinear crystal having chi2 nonlinearity, and it gives birth to pair of photons which are called signals and idlers. And these photons, generation of these photons requires to satisfy certain conservation relations which are momentum and energy conservation. In fact, if you look into how the profile of these photons looks like when we take a camera and look into that. So this is not an ordinary camera, it's a camera which is sensitive to single photons, which I just showed you in the previous video. So you see that these are the ring type structures which you can get from these for different phase matching conditions. This is type 1, where the polarization of the photons are same, and this is type 2, where each ring produces its own polarization. So if the left ring is horizontally polarized, the right ring is vertically polarized. And at the cross sections, as you could see, that the photons can come from both the rings. So at the cross section, the polarization is not defined because we do not know whether the photon comes from the left ring or the right ring. If it comes from the left ring, it is horizontally polarized. If it comes from the right ring, it is vertically polarized. However, if I measure a photon here and it is horizontally polarized, I immediately know that at the lower portion, the photon would be vertically polarized because it will come from a different ring. So this kind of structure is essentially giving us what we call polarization entanglement. So what is entanglement? I will try to explain you from this cartoon. So suppose I have a state which is written as HAVB minus VHB with some normalization. H is horizontal polarization, V is vertical. So if a photon, if this is a photon source which is producing two photons A and B, A goes to the left side, B goes to the right side, and let us say that these photons are traveling very large distances, say one is in this galaxy, other one is some other galaxy, and I make a measurement of polarization by using a polarization beam splitter. And if A is horizontal, that means if A gets transmitted, the B will be reflected because it is vertically polarized. You see that they are always behaving in an opposite manner. Now the next photon, If it comes to this side and it is reflected, that means it is vertically polarized, the other will be automatically horizontally polarized, the way it is prepared. So clearly you see that the entanglement offers us a way by which, despite the two systems are not together, they are very, very far apart, by knowing the property of one can immediately derive the property of other. And this simultaneous knowing the information is a unique trait of quantum entanglement, and one can use it even for quantum communication. So we have now two kind of systems. One are using these single photons, which I already explained, which are called prepare and measure kind of systems, and they can, there one is preparing the state, other one is measuring the state, and this is called prepare and measure QKD. The other one is entanglement based QKD, where you are generating an entangled photon source. That means two photons, you are sending one photon to one direction, other photon to other direction, both are measured by Alice and Bob, and then they can do the communication. So these are the several benefits of these, each of them. So for example, the prepare and measure systems are essentially derived from the classical kind of communication, so they have higher rates compared to quantum, purely quantum systems like quantum entanglement based systems as of now, because quantum entanglement based systems are still in development. However, they can lead to several security benefits compared to prepare and measure. For example, they can make trusted node free communication. You do not require any carrier, you do not need any trusted node. You can do long distance communication using properties such as quantum repeaters and quantum memories, and this all can be done using quantum entanglement. The another feature with quantum entanglement is that even the source which is producing those entangled photons can be hacked by any adversary, but as long as it is producing entangled photons, you can always do communication, quantum communication with that. So what essentially I'm trying to to infer is that entanglement based QKD is quite new. It is under development. However, it has a huge potential to do several tasks which are beyond the scope of prepare and measure, which include not only security but also quantum teleportation, quantum metrology, and also developing trusted node free communication. Now, I will give you examples of some protocols from prepare and measure and entanglement. So one of the protocol for prepare and measure is distributed phase shift protocol. I'm sure you must have heard about it in previous talks. Here we are using a laser which is attenuated using some attenuators and also modulated so that you get pulses. So now you have pulses of few megahertz of rates. You send them through the quantum channel, and you use here a 1-bit delay interferometer where the photon interferes with its previous pulse, because you are sending these pulses. So every photon interferes with its previous pulse, and the relative phase between the two will decide whether the photon is detected by detector 1 or detector 2. So here these pulses which are produced by Alice would be given phases randomly, either 0 or pi, and depending on the phase difference, if it is 0 0 or pi pi, depending on that, the detection would be either detector 2 or detector 1. So now once the clicks are obtained here, you can take the timing information of these clicks, you send them back to Alice, and Alice has its phase references, and from that she can know that what timing information will provide what key. So now you have the keys with Alice, you have the keys with Bob, and that way you can do the communication. So this is a very, very simpler communication method or DPS protocol. And the good thing is that it is very robust against photon number splitting attacks, and also it is using the phase information. So this is very, very optimal for fiber based communication, because in fiber the polarization may be scrambled but the phase remains the same. So that way you can do communication with fibers. The other protocol is using polarization entanglement, and I'm sure that you must have also heard about it. Here, as I said, that an entangled photon source sends one photon to Alice, one photon to Bob, and there is the polarization measurement which is done in Alice side as well as Bob side using some standard basis selectors. So it is either a horizontal polarization or vertical polarization, and the other one measures a diagonal which is either positive or negative, anti-diagonal. So these kind of measurements can be made. So these are some tables where it tells you that when you have a particular basis and a particular measurement is made, then what kind of output is expected. And by looking into these outputs, you can check with the preparer and see that after shifting whether the bases were same or not. If the basis were same, you will take that data, but if it was different, you just discard the data, because that means that you had some you have randomly put a wrong outcome. Now once the bases are same, you can encode the information, invert them, because you are using a anti-correlated scheme, so you have to invert one to make it correlated, and finally that way you can look into for errors, and after post-processing get the final key. So both of these protocols, prepare and measure and entanglement based protocols, they can be used for quantum key distribution. Now, if you look into the state of art QKD networks, which are the next stage after point-to-point communication, then there has been several developments in this domain, including the first QKD network, which was developed by Tokyo in 2010. And you could see that this network was connecting several types of communication between the different cities, and the total length was about 220 kilometers. And these are the raw plans of different distances along with the management. So they basically made a network where they had a physical layer, then there was a key management layer where the key can be managed, and finally from the key management you can do the communication. So you had a communication layer, and they used several key management servers where the keys can be stored and can be taken out. China has recently developed a very, very huge network, more than 5,000 kilometer, which is using both fibers as well as the free space, which is connecting to satellite. And it's what we call China's backbone network. And this kind of network is also very, very useful. In fact, they are looking for their commercial applications from 2027, especially for banking and financial sectors. And what it essentially tells is that there is a need of multi-node quantum networks, which can be finally used for deployment and for final applications, and they need to be compatible with the existing QKD architecture, and in fact existing infrastructure as well, because already we have a lot of fiber which is being used for classical communication. So if the same fiber can be used for quantum communication, it will essentially save a lot in terms of the monetary requirements. Now once you have developed these networks, these small networks at different regions, then you would like to connect these networks through a bigger network, and that is what we call quantum internet. It is a quantum network of all these small quantum networks. And the good thing with quantum internet would be that all what you develop as a network would be a precursor for the final quantum internet. And here you require quantum processors, which will be essentially these quantum computers. You want to securely communicate between a quantum computer with another quantum computer. That means you need to communicate through qubits. So you need quantum communication to do that. You need quantum switches or other kind of quantum network devices, which will be connected at different points, such as the switches or the routers or other kind of resources. You need quantum repeaters so that the information from an intermediate node can be sent to the next node. And that way, this kind of network would be a parallel network with existing classical internet, because both classical and quantum internet would be supplementing each other. A person for every day-to-day use would not require a quantum internet. It will still use its classical internet, but there will be an interoperability between classical and quantum, so that if you work for some very, very sophisticated requirements, then you would use the quantum internet as a supplementary access. Uh, Now, since I'm going to discuss about optical fiber as a quantum channel in my next talk, I would just give you some precursor on that. That first of all, a fiber network is a silica or glass-based fiber, a network of fibers, and each of the fiber has is essentially single mode. It has a dimension of a few microns, 5 to 10 micron, and there is a glass core inside with a cladding outside. The core has slightly higher index than the cladding, so that you can have the total internal reflection, and light which is entered from one side can take multiple reflections and come out from the other side. Now, the standard losses in that kind of optical fiber are about 0.2 dB per kilometer. So if you have, for example, 100 kilometer, the losses would be 20 dB. And this is a loss in a standard fiber which is not in the field. If you put fibers in the field where they are either having a lot of pressure or having a lot of cuts and splicings, then the losses would increase very, very drastically, and then the losses can be 0.3, zero point 0.4, or even 0.6 dB per kilometer. The low loss wavelength is 1550 nanometer, which is typically called the telecom wavelength, and this is the wavelength at which we try to do all kind of quantum communication in fiber. We can go for long distances by splicing the fiber, and the good thing is that this guided propagation allows us to go for as long as distances we could, uh, provided by that the loss limitation can be addressed. And then if we compare it with the free space communication, then for short distances one prefers to use optical fibers because the losses are limited and very low compared to a free space communication channel. However, if you go for very large distances like few hundreds of kilometers, then the losses, which are exponentially increasing in the case of fibers, would be very high compared to a free space communication or a satellite based communication. So this is why fibers are typically considered to be a best candidate or best medium for a small distance or medium distance, typically for between the cities or intercity kind of communication. And if you want to go for even longer kind of communication or long distances, then you would like to require the satellite based communication. And this is something which is showing that a very large amount of data transfer can happen with fibers. The bandwidths are very large, and these are the different ITU bands from O band to U band, with the wavelength starting from 1250 to something 1650 nanometer. So you have a large range of wavelength. Typically C band or L band is used for fiber based communication, and sometimes O band for classical communication. Now, there are several open challenges in quantum communication, and I will complete my talk by just giving you some highlights of the challenges. So first of all, as I mentioned, that the security is a very, very important issue in case of QKD. However, how secure we are will actually depend on how good is our system or the practical system compared to the theoretical assumptions. So if our system follows exactly the same theoretical assumption, then the security would be very high. However, if there are loopholes, then the securities would be compromised. Quantum hacking is a completely new domain where people are trying to utilize those security loopholes for breaking the codes, and this is why one needs to provide several kind of countermeasures so that these hackings can be stopped. Trusted nodes, as I mentioned, are these security loopholes, because they're theoretically they are trusted, but in principle they can be untrusted as well, and one requires to use quantum repeaters or quantum memories by which a long distance communication can happen. Similarly, we need to develop quantum interconnects, because as of now everything is made for classical communication or fiber communication and if we want to do quantum communication, we really need to make dual use technologies. We need to make hybrid networks where fiber and free space, both kind of networks, can run parallelly, and also management of key can happen. And one also requires to exist QKD, that is quantum communication, coexist with the classical communication, because that will save a lot of optical fiber. As of now, we are using two separate fibers, one for classical communication and one for quantum communication. However, if both can be multiplexed and can sustain on a single fiber, then a lot of infrastructure can be saved. And finally, one needs to develop trust and adoption of these technologies in a public domain, because as of now people prefer to have the existing technologies which have been well tested compared to a completely new technology like quantum communication. So if such trust can be developed, then probably quantum communication can move forward in a very, very rapid manner. So to summarize, we discussed about the quantum revolution and some quantum technologies and their future aspects. We discussed the protocols associated with QKD and what kind of experiments people are going for with single and entangled photon sources. And finally, we discussed that what is the need of QKD networks and quantum internet, and what are the different challenges in QKD. So with this, I stop my first talk, and if there are any questions, I would be happy to answer them.
There are few questions for you. So
Yeah.
should we dictate, sir?
So the
You can see them?
questions are in chat, I see. So are they only in chat, or there are some verbal
Yes,
communication?
yes. They are on the chat only.
Or they are on the chat only? So I think we have to go through one by one to them. So there is a question which I we could see. What will be the beam width of laser source? What when photons are sent through fiber, do they undergo scattering and dispersion? How these effects are mitigated, which are directly impact on error rates? So the beam width of laser depends on the application. If I'm doing a free space communication, my beam sizes would be completely different. If I'm going for longer distances, the beam sizes would be even bigger. Typically, if the question is associated with free space communication, because then only we talk about beam width, then the sizes are typically few tens of millimeters to few centimeters, typically 5 centimeters up to 5 centimeters. And the second part, which is asked, that whether they go for scattering. Yes, they do go for scattering, but whatever we have talked in terms of the loss size 0.2 dB already includes scattering effects. However, dispersion is not included, and dispersion happens, and it depends on several factors. If I'm using a very, very narrow line width laser, the dispersion would be very, very less. And typically, we prefer to use as narrow as possible, so that we do not require to put any additional optical components to reduce the dispersion. But we can also use dispersion compensating fibers, by which we can reduce the dispersion. And if we do that, which I will talk in more detail in my second talk, you will see that it really reduces errors significantly. Then there is question, is that can you describe more about fibers which are used for polarization? So we are using, as I mentioned, that we are using the standard fiber. So we are using the same fiber which everybody is using at their home for fiber communication or internet one, with the optical fiber, that is the standard telecom grade fiber. So we are not using any different or a different type of fiber, because the goal is to be off the shelf component, so that we can be compatible with the existing infrastructure. And then the question further asks that which color wavelength are used. As I mentioned, that we are using telecom wavelength for fibers, where the losses are minimum. So it is 1550 nanometer or around 1550 nanometer. Then there's a question, is which Indian manufacturers produce these fibers? So there are several actually. Sterlite is a big company, for example, and then there are many other ones which are producing. So there are fiber production in India is significantly mature now. So there is no problem in producing or in getting Indian fibers, for example, for doing these experiments. Then there is a question by somebody who says that how to deal with photon loss. And then I do not understand what it says. There is some dash dash dash. Uh, as no cloning is possible, how quantum repeaters work? No, so repeaters doesn't work in that way, because of course the cloning is not allowed. But I have not specified what quantum repeater is. But you just think of that there are two entangled photon sources. One is producing entanglement between A and B, other one is producing entanglement between C and D. Now, if by any means I can interact with B and C in such a way that they could be entangled together, then automatically my A and D will also be entangled. So this is the exact way by which we do quantum entanglement. We use quantum entanglement for quantum repeaters. So we do not clone anything. We just try to entangle the different particles using a process called entanglement swapping. And by swapping the entanglement, we can show that the different parties, the remaining entangled photons, can be also entangled. However, the limitation here is that since these photons are not every time available, you have to wait for the photon. That means you need a quantum memory, and as of now, there are no successful long-term quantum memories, and this is the reason that quantum repeaters could not proceed with that rate for toward their development. Photon generation input source is different from normal optical fiber light source. I don't know what it means, normal optical fiber light source. So I told you that, and there is also, it says that what type of source is used in the recent achievement of 1 kilometer. Okay, I'm not specifying on this free space communication because I was given a topic on fiber based communication. However, still I would answer your question. So you are asking what kind of source has been used. So we still use that entangled photon source. It is an entangled photon source, but it is not working at 1550 nanometer or telecom wavelength. For free space communication, we have been using a source at around 810 nanometer. But it was still a entangled type 2 entangled source, and it was entangled in polarization domain. And then there is a question, SPDC source. Yes, as I mentioned that the process by which we develop is SPDC. We do not use BBO because BBO is a bulk crystal and it is a very less efficient one. We use periodically poled crystals. There are crystals called periodically poled lithium niobate, which are normally called waveguides. There are crystals also available, but they are waveguides called PPKTP or PPLN, which basically we use for SPDC where the efficiencies are very high. So I think most of the questions I have answered. If there are any questions, I will answer in my second talk. So I can maybe stop sharing. I
Yes.
already stopped sharing.
Yeah.
Okay. Yeah.
So we can take 5 minutes break, sir.
Perfect. Perfect.
Yes. So we will connect at 3:05. Okay.
Okay. Thank you.